Okay, so lesson 2.3, adding and subtracting radical expressions. When we look at adding and subtracting, it's very similar to treating it like a variable. So we're looking for like terms or like radicals in this particular case in order to be able to add them together. They also need the same index in addition to their radicand. Again, in terms of remembering that terminology, this whole thing is a radical. This little piece here is the index. And here, this value is our radicand. So when we look at this example here, we see that we've got root 3 and root 3 here. Root 7 is different, and so we won't be able to combine those together. So it's rearranged. This is a step you can skip if you want. Okay, but the key idea is to say 1 plus 4 is 5 root 3's, and then just 2 root 7's are left over separately. So always looking for like radicals. In this case, we already have our like radicals formed. So 9 minus 5 is 4 root 5. That's it. B is a little bit more complicated because we are actually going to have to define our like radicals for us. So we're going to be looking for perfect cubes that go into these numbers. So for 24, it might be easy to spot. Okay, well, that's 8 goes into there. Cube root of 8 is 2, so I've got 2 cube root, and then it's 8 times 3, so that's what's left underneath. 192 might be a little bit harder to define. If you want to prime factorize that, 296, 3, that's 32, 8 and 4, 2 and 4, 2 and 2, 2 and 2 from here. So prime factorizing, I want to find how many cubes I have. Well, I've got 1, 2, 3, that's one perfect cube. 1, 2, 3, that's another perfect cube. So I've got 2 as a cube, 2 cubed, so I can take that up twice. I'm going to be left with 3 underneath. So minus 2 into 2 cube root 3. And then 375, I'm going to have to do the same thing. So I'm just going to do that over here. I'm going to take up 5, maybe even 25 would be more effective. And I've got 5, 5, 5, and 3 again. This is our cube. So we've got 3 cube root 3 again. Now you'll notice that all of our radicals are the same. So when we go to simplify this, we've got 2 minus 4 minus 3. 2 minus 4 is negative 2, minus 3 is negative 5 cube root 3. And so that looks like a much more manageable number, a number that we can wrap our head around, whereas in our initial question, I couldn't imagine kind of where those values might even end up. And in addition to that, we couldn't actually manipulate them without a calculator. As you know, this unit is entire calculator free. Square roots, we're at least a little bit more familiar with. So 63 is a product of 9. That simplifies to 3 root 7. I've got 4 can go into 40 10 times, so that's going to be 2 root 10. I got 9 can go into 90, so that gives me 3 root 10, and 9 goes, in terms of 28, we're looking at 7 times 4. And that simplifies to that. From here, I've got 3 minus 2 is going to give me root 7. And then 2 minus 3 is going to be negative root 10. So that'll be my final answer. So always looking to simplify those radicals, get them in their lowest form, and then we're going to look to combine them. When we add variables in there, it actually has the same impact. We're still going to want to simplify where we can, look for matching radicands and indices so that we are able to look at the coefficients. So in this case, it's a, root of a, root of a, root of a. They all match. So I've got 6 plus 5 is 11 minus 11. This is actually all going to be 0. Do be careful to state your restrictions on your radical as well. Okay, don't forget that. Just because it doesn't ask for it, always state any restrictions. So a would have to be bigger than or equal to 0. And we saw this in our last lesson because we cannot take the square root of a negative number. Looking at the next example, because we don't have that similar radical to start with, we've got some similarities, that a squared times b. We've got values in there as well. So we want to simplify this further. So 50 is actually 25 times 2, and 8 is 4 times 2. So I'm going to break that out. A squared is also a perfect square, so I'm going to take that out of my radical as well. So I've got 5a, then the square root of 2b, minus 2a, and the square root of 2b. So again, using your understanding of perfect squares to take those out of the radical. Now we see these guys are matching, same index. So 5a minus 2a is going to be 3a, and our radical is unchanged. In this case, we would say that b has to be greater than or equal to 0. But a could be an element of the real numbers because it's squared, which means it's always going to be positive. Our last one in this example is a cube root, but the same principles apply. 27 actually is a perfect cube, and so is p cubed. So I'm going to take the cube root of that, which is 3p cube root of q, plus 8p and the cubed root of q. Again, doing this allows me to get that matching radical. 3 plus 8 is going to be 11p and the cube root of q. Radicals are always unchanged. Kind of like a denominator when you're adding fractions. Once you've got a common denominator, that denominator doesn't change. Same thing happens here. So again, we're seeing the same process. We're going to use the same goals. Just looking to identify matching radicals. So in this case, 7 minus 3 is going to be 4 root m plus 7 root n. And then we still have these restrictions carrying through. N and m must be greater than or equal to 0. Same idea here. Watch for your indices in this case. It looks like these are all the same, but in actuality, we're talking about the cube root in this case and the square root here. So 2 minus 9 is going to be negative 7 cubed root of negative 3b. And then 8 plus 3 is 11 square root negative 3b. Again, with that restriction that b is less than or equal to 0. Now that restriction comes into play not because of the cube root, because that's allowed to be negative, but again because that square root cannot be negative. Finally, we get to this last example. You're going to want to try and simplify this. Pause the video, give it a shot on your own, and then reopen the video and we'll see what we can do. Okay, so when we go to look at this number, we're again looking for any perfect squares that we can find out of this. So 32, just as some notes for myself, I'm looking for the biggest perfect square in it. That is 16 times 2. A will also break down into a to the 4 and a. And anytime we have an even number of exponents, we do have a perfect square, because a to the 4 can be broken down to a squared and a squared, both of those being perfect squares. 45 again can be broken down by 9 and 5. B cubed can be written as b squared times b. 125 is 25 times 5. B is already as low as it can go. And finally, 72, same as 9 times 8, which actually can be broken down to 4 and 2. So we've got two perfect squares in there. And then a can be broken down to a squared and a. So we've got lots of perfect squares that we can simplify out of here. So when I go to just write the simplified version of this, where my radicals are, for lack of a better term, reduced, I'm going to have 3 times 4 times a times a. And all that's left under my radical is 2 and a. For my second term, it's minus 2 times 3 times b, and I'm left with 5b underneath, plus 5b times 5, and I'm left over with 5 and b. Box those instead, so keep track of the difference. And finally, minus 2a times 3 times 2 a, and all we're left with is not 8, but 2a. So we want to simplify this even further before we continue and try and match things up. We've got 12a squared root 2a. I'm going to rearrange this so that they're beside each other. So 2 times 2 is 4 times 3 is 12, so minus 12a squared root 2a. Then I've got negative 6b root 5b plus 25b root 5b. Now I need to check not only my radicals, and I've got these two matching and these two matching, but I also need to check their variables. They are all consistent. So a squared, excellent. So these two are truly like terms. Now 12 minus 12 is 0, so they cancel out. B and root 5b, b root 5b, these two are also like terms. Negative 6 plus 25 is going to give me 19, b root 5b. And that will be my final answer, along with those restrictions of a and b needing to be greater than or equal to 0. So that's this lesson, short and sweet. Give some practice to all of these, especially the simplifying of your radicals and then looking for like terms. That's going to be your challenging part. Remember, if you have questions about prime factorizing, definitely ask, or you can Google prime factorizing, and I'm sure there's lots of videos out there.